Hey guys, Kenna here. So today we're going to take a quick look at wave basics. So these are some of the things you should probably take with you as we go through and talk about sound, light, electromagnetic waves in general, just in terms of the properties of waves. And then from there, we'll go ahead and start looking at more detail at the different types of waves. But we'll give you the basics here. All right, so essential questions for today. Number one, what is a wave and how do you describe its motion? So we'll talk about some terminology that you might have heard before, but we'll try and put it into terms that make it really clear as to how to go ahead and do these in terms of wave properties. And two, what are the similarities and differences between longitudinal and transverse waves? These are going to be our two most common wave types. There is a third that we'll introduce you to that's called surface waves, but we'll start here with our two main types of waves. So first things first. What's a wave? What causes waves and how do they travel from one place to another? Today we're going to guide you through the basics of waves. We'll discuss their origins from vibrations, remember simple harmonic motion that we talked about before, and then we'll look at how they carry energy through a medium. So, as a definition, if you were to look in back of your textbook, a wave is a traveling disturbance that carries energy from one place to another. So, really, when we're talking about a wave, we're looking at the movement of energy. Now, do not mistake the movement of the wave for the movement of the medium. For example, water or in anything else on the medium, such as a boat. So, if you were to watch a buoy that's sitting out on the water, the buoy seems to go up and down, but ultimately, while the energy moves through the water, the waves itself, the water, doesn't really move. It stays essentially in the same place. So if it goes in this kind of forward and back motion, this harkens back to our simple harmonic motion we introduced you to last time. Any movement that follows the same path repeatedly is called a vibration. As such, waves are an example of simple harmonic motion. The velocity of a wave depends upon the medium through which it is traveling. The velocity of a wave is in a given medium is constant. So depending on what the material is that the wave is traveling through, it's going to have a fixed speed. Now, the velocity of sound in air depends on the air temperature. So the speed of sound in dry air is 331.5 meters per second at 0 degrees Celsius. And while that may seem fast, we start realizing that we've experienced instances where sound is delayed. If you've walked up from a distance on a basketball court and you've seen somebody dribbling a basketball, and then you start realizing that the sound of the ball hitting the ground is out of sync with what you're seeing, that's because light travels so much faster than sound does. So, as you increase the temperature, though, the speed of sound actually increases about zero point 0.6 meters per second for every 1 degree Celsius in temperature rise. And this should make sense because what's temperature? Okay, think back to what we talked about in matter and thermodynamics. Increase in temperature means the particles are moving faster. And as such, there are more collisions, which makes it easier to transport sound energy in terms of air pressure. It's going to move through the air faster. Now, the velocity of different mediums is generally going to be faster in solids and slower in gases, but there are some exceptions to these rules. Here's a table with the speed of sound in a couple different mediums. If you look at air, you'll notice that the speed of sound is 347 meters per second. Now, when you get to aluminum, that travels at 4,877 meters per second, so a lot faster. Okay. And so there's cork, water, and brick, and I'll let you take a look at it. So today I want to make sure that you understand the basic parts of a wave so that when we refer to them later, when we're going over sound waves or light waves, that you understand how these parts are appropriately labeled. Let's start with the crest. So the crest or peak is the highest point on a transverse wave. The trough then is the lowest point on a transverse wave. The rest position of the wave is called the node or nodal line, and the wavelength is the distance from one point on the wave to the next corresponding point. So let's say one peak to another peak. The next thing I want to go ahead and take a look at is what's known as the amplitude. Now, the amplitude is the height of the wave from the rest position to the peak. Okay. Some people will go ahead and label it from peak to trough, but that's actually an inaccurate measurement of the value. What we're looking at is the distance from the nodal line or the rest position to the highest peak in terms of the crest. Okay, so that's the amplitude. When we go ahead and start looking at frequency, frequency is the number of wavelengths per second. Okay, how many times does this wavelength go through in 1 second? All right, and if we think about that, that is going to be related to the period. Okay, and so frequency and period are related by an equation I'll show you here in a minute. Now, we're looking at what's called a transverse or sinusoidal wave, and this is the typical kind of wave you'll see in your math classes. But this is not the only major type of wave that we're going to be dealing with here in physics. A wave in which the motion of the medium is at right angles to the direction of the wave is called a transverse wave. And so these are the waves that you've seen. You typically see them going up and down. And when you look at ripples inside the water, you're seeing exactly that sort of structure. So this sort of structure where it goes up and down and up, okay, the energy is moving forward. The wave medium is going this direction, but you'll notice that if we draw an arrow, the movement of the wave is going this way and this way. So it's perpendicular to the motion of the wave. Okay, so again, energy is traveling to the right in this example, and the wave itself is traveling up and down. And we'll talk more about this when we go over light in a later class. Okay, all right. So the other type of wave we want to go ahead and cover or talk about is what's called a compressional wave or a longitudinal wave. Now, a compressional wave, the area gets squeezed together in areas known as compressions and spread out in areas known as rarefactions. This wavelength corresponds the same way to what we saw in a transverse wave. So essentially, the rarefaction is like a trough where there's a lot less, and the compression is like a peak where there's a lot more of the material together. Okay, now in class, we would typically go ahead and do this with nice little demos and start looking at how we can go ahead and change frequency of a standing wave and all these different features. But for now, let's just make sure we understand that there are two different types of wave categories. We have compressional or longitudinal waves, and we have transverse or sine waves. This is what compressional waves look like, and the sine waves go at perpendicular angle to the direction of the motion. I would like, however, to go ahead and highlight that on this example, your wave energy is traveling in this direction. So in this case, your rarefactions and compressions travel in the same direction as the energy flow. So we'll label that energy. Okay. That yellow is a little hard to see, so you'll bear with me. Okay, so as I mentioned, this is also known as a longitudinal wave, and the motion of the medium is parallel to the direction of the wave. While light is a good example of a transverse wave, sound is a good example of longitudinal waves. The other category that I mentioned is what's called a surface wave, because not all waves are simply transverse or simply longitudinal, but are a combination of the two, and these are what we call the surface waves. Ocean waves are an example of surface waves. Earthquakes are another example of surface waves. And they typically happen at the place where one medium meets another. All right, so here is another equation for us to go ahead and make sure we know. That is the relationship between amplitude and frequency. Now, amplitude is the height of the wave, and this is about how much energy is being carried by that particular wave. So the bigger the peak or the more material in the compression, the greater the amplitude. And in terms of sound, this would be represented by volume. Okay. When we look at frequency, that's how many times that little wavelength goes through. In sound, this is going to be representing the pitch. Shorter frequency, okay, higher the pitch, longer frequency, lower the pitch. All right, but we'll talk more about that when we go ahead and get to those in our sound notes. All right, so two quick little videos going ahead and reviewing the properties of transverse and longitudinal waves, and then we'll go ahead and finish up.
Waves carry energy, but not matter, from one place to another. For example, a rock thrown into a pond next to a bobber causes the bobber and the pond water to move up and down, while the energy waves generated by the rock move towards the shore. In other words, the bobber and pond water, which are matter, remain in the same position on the pond, while the energy carried in the wave travels across the pond to the shore. The action of the wave on the water is perpendicular to the direction of travel of the energy along the wave. If we fix a rope at one end and move the other end, we can also produce waves. The waves produced by throwing a rock in a pond or moving a rope up and down are called transverse waves. Transverse waves have a number of characteristics. A trough, which is the low point of the wave, and a crest, which is the high point. The difference in height between the crest and the trough of the wave is the wave's amplitude, and the distance between the crests is...
Now, please remember that that's not how we measure amplitude. It's from the nodal line or rest position to the peak, not from the peak to the trough. Okay.
referred to as the wave's wavelength.
Okay, so let's go ahead and take a closer look at longitudinal waves, and then we'll go ahead and finish up this set of notes.
A second type of wave is a longitudinal or compression wave. In a longitudinal wave, the particles of the medium carrying the wave also move back and forth. Unlike transverse waves, however, the particles of the medium move in the same direction the wave moves, not perpendicularly as in transverse waves. If a sharp force is applied to one end of a spring, a longitudinal wave travels along the spring. The wave moves the spring's coils closer together as it passes along them. After it passes, the coils move apart again. The areas where the particles are closer together are called compressions, while the areas where they are farther apart are called rarefactions. The wavelength of a longitudinal wave is measured between the center of compressions or rarefactions.
Okay, so that's the basic properties of waves, and next time we'll go ahead and talk about sound. Remember, the sound is a longitudinal or compressional wave caused by vibrations in air pressure, producing vibrations on the tympanic membrane or eardrum. And we'll look at that next class, and then we'll go ahead and take a look at more information on light waves as well. Okay, have a good one. Take care of yourselves. Stay healthy. Stay safe, guys. I'll talk to you soon. So long.